This is part 8 of the series, An Introduction to the Derivative, and in this part we're going to explore implicit differentiation. Now, up to this point, what we've seen is functions in two variables where one variable is explicitly defined in terms of the other. For example, if we have something like y equals 2x squared plus 3x minus 2, y is defined explicitly in terms of x. However, this isn't always going to be the case. We could have a function such as something like this, where we'd have x, y plus y equals 3x. In this case, we have y implicitly defined in terms of x. And there are some times when you can manipulate your equation or your function so that y is explicitly defined in terms of x. But in some cases, this is either extremely difficult or impossible, such as the following case. X squared minus 2y to the third plus 4y equals 2. Now, this function would be extremely difficult to represent explicitly in terms of x. But we can still differentiate this function. And we do this using a concept called implicit differentiation. Let's first consider a simple familiar derivative. Let's take the derivative with respect to x of 2x. Now here you can see that the variable matches the variable of differentiation. In this case, we can differentiate as usual, and the derivative is simply 2. But now let's take a case where the variables do not match. So let's take the derivative with respect to x of y squared. Now in this instance, our variable of our expression does not match the variable of differentiation. In this case, what we have is some function y which is implicitly defined in terms of x. That is, we don't know what this function y is, but it's some function of x that we could figure out perhaps in the future. So in essence, what we have here is an example of the chain rule, where we have some u substitution. So in this case, if we want to differentiate this, we differentiate implicitly, which means we're using the chain rule to differentiate this expression in terms of x. So to show you how that works, we're going to apply the general power rule. So this is some function y squared. So we take the 2 out front, and we copy the inside function unchanged, take 1 away from the exponent, so it's to the first. Then what we have to do is, in the chain rule, we have to take the derivative of the inside piece. And the derivative of the inside piece is dy dx, the derivative of y with respect to x. And so our final result is simply 2y dy dx. Now, the reason this is here is because by the chain rule we had to take the derivative of this implicitly defined function of x without knowing what the function is. So we don't know what it is. When we can find it out, the derivative of it will go right here. So this is basically a placeholder for the derivative of this implicitly defined function. So let's go ahead and try a few more of these just to make sure that we've got this idea down. So what I want to do here is we'll do one very similar to the one we just did. So d over dx, the derivative with respect to x. This time we'll do y to the third. So again, our inner function is y, our outer function is something to the third. So we're going to employ the chain rule. So it's 3 times the inner function. Take 1 away from the exponent, 2. Now we take the derivative of the inside piece, and we can either use the Leibniz notation, which is this, or we can use Lagrange notation, which is y prime. Either one works. It just depends on which one works best in a particular situation. And as we move forward, you'll see situations in which Leibniz will be the better notation and others in which Lagrange will be the better notation. So simplifying this, we just have 3y squared y prime. Again, this is simply a placeholder for the derivative of this implicitly defined function of x. Now we'll look at another example, which I'll copy offline so you don't have to see me struggle to write it. So our function is y to the third plus y squared minus 5y minus x squared equals -4. And let's go ahead and differentiate this. So here, general power rule. So this is going to be 3y squared y prime. I'm going to use Lagrange because in this case it'll be a little cleaner when we simplify our terms, plus 2y y prime minus 5, and the derivative of y is y prime. Minus this we differentiate normally because it matches the variable of differentiation. So that's just 2x. And the derivative of a constant is 0. Now, to simplify this, we need to gather up all of our y prime terms because we're trying to find the derivative of this function. So we need to solve for y prime. So here, luckily, we have 3 terms all with y prime, so we can factor the y prime out. And we're left with 3y squared plus 2y minus 5 minus 2x equals 0. Now we're going to add our 2x to the other side. So we have y prime times 3y squared plus 2y minus 5 equals 2x. And now we're just going to divide by this other term. So y prime equals 2x over 3y squared plus 2y minus 5. And there is our derivative. So let's try another example that I'll write off screen. So here's our function, and we want to find the slope of the tangent line at the point square root of 2, 1 over the square root of 2. So we're looking for slope, so we need the derivative of this function. So we're going to derive this implicitly, and we have 2x plus 8y y prime equals 0. Again, this variable matches the variable of differentiation, so we just differentiate as usual. Here we have the general power rule because we have an implicitly defined function of x here. So 2 times 4 is 8. Y, subtract 1 from the exponent, times the derivative of the inside piece, which is y prime. Derivative of a constant is 0. So now we want to solve this for y prime. So 8y, y prime equals negative 2x, y prime equals negative 2x over 8y. Simplify this out, and y prime equals negative x over 4y. Now this function gives us the slope of the tangent line of this function, and so that's all we have to do is substitute this value in for x and this value in for y in this expression, and we will have our slope. So we will take negative square root of 2 over 4 times negative 1 over the square root of 2. So this gives us negative square root of 2 over negative 4 over the square root of 2. And these negatives disappear, so this is going to be a positive expression. And we can convert this from division to multiplication by inverting this. So what we have is square root of 2 times the square root of 2 over 4, which is 2 over 4, which is 1/2. So the slope of the tangent line of this function at this point is 1/2. Let's go ahead and do another one like this, just to solidify our concepts. So here we're looking for the equation of the tangent line of this function at square root of 2 over 2, square root of 2 over 2. So to begin with, rather than use the product rule, I'm going to go ahead and multiply this through to simplify this. So we have x to the 4th plus x squared y squared equals y squared. Now differentiating, I have 4x to the 3rd plus, we actually have a product rule here anyway, so this is u dv plus v du. Equals the derivative of this piece, which is 2y y prime. Now to continue, we're going to group all of our y prime terms on the left. So we have 2x squared y prime minus 2y y prime, I just pulled this over here, equals, and these are going to the other side, minus 2x y squared minus this piece, 4x to the 3rd. Factor out a y prime. Y prime is 2x squared y minus 2y equals this piece, negative 2x y squared minus 4x to the 3rd, and then divide by this piece. So y prime equals negative 2x y squared minus 4x to the 3rd over 2x squared y minus 2y. To save time here, I divided every term by 2 and factored out an x out of the numerator, actually a negative x, and factored out a y out of the denominator. If we evaluate this at this point, we get 3. Taking this point and slope and putting in point slope form, here's our equation, and this is our equation in slope intercept form.